Hi, and welcome to Double E's Talk Tech. My name is Daniel Bogdanoff, and we are streaming live from Keysight in Colorado Springs. Thank you for bearing with us. We got hit by a blizzard today, so the office is pretty much empty.
It's a little crazy out there.
Scopes in an RF environment, but those people literally couldn't make it into the office today, or at least they said they couldn't. I don't know. We'll see. You can ask Brig later about that. But Jesse is my clutch savior here, so thank you, Jesse. Jesse Rebeck is on the ASIC team.
Correct.
And can you tell us a little bit about what you do on that team?
Yep. So my name is Jesse Rebeck. I manage the ASIC packaging team here in Colorado Springs, which is part of the ASIC technology organization here. You hear the word packaging and you immediately think things like bubble wrap and cardboard boxes, but actually what we're talking about is the sort of the interconnect systems that would surround the die and interconnect it to the rest of the system. It also serves, which we can talk a little bit about.
Yeah.
But yeah, that's what
I think packaging is really, they're kind of the unsung heroes of the IC world, where you think about like a chip and all the logic and analog or digital, whatever. We've covered that in other podcasts. But all of that has to get placed in something that's actually usable. So
with high signal integrity, with good thermal management, with high reliability.
Yeah. So like without the packaging teams, chips just don't work. Like you can't actually implement them.
Correct. Right.
So
various ways to do it.
Yeah. So can you tell us about those ways?
Sure. So traditionally, chips were interconnected to other system bonds. Every die has a series of I/O, and you would use very small wires to interconnect those pads on the die to a lead frame or something like that. It could be a ceramic, and so that's one way to do it. There are limitations with that in that you can usually only wire bond to the perimeter of a die, so you're limited in the I/O. Also, wire bonds introduce some parasitic inductance into your signal path.
That makes sense.
So that's going to degrade your signal integrity in some cases. When you want to integrate more and more onto your IC, you would traditionally move to flip chip packaging.
Flip chip. Okay.
Is
that like flip cup, or is that different?
Very similar, but subtly different. So yeah, there are lots of buzzwords in packaging. We can talk through some of that. You'll hear all kinds of different terminology, and sometimes they mean similar things or the same thing. So you have to kind of watch out for that.
I assume flip chip is a buzzword.
Or what you can call it that. So really what it means is that instead of your die being dead bug, you call it dead bug, meaning that the pads are facing up and your wire bonding out.
Okay.
Your chip is now live bug. It's flipped over. It's alive. It can walk around on its pads, or what we call bumps.
Okay.
They're bumps of small solder balls that are electroplated, or more recently, technology has emerged that uses copper pillars.
Pillars.
Yep. So instead of being balls, they're cylindrical. Huh. And
how do you fab something like that? Like, is that a via that you etch around, or
they're electroplated?
Okay.
Typically. So it's done at the wafer level, and you would plate up these bumps with a mask patterning kind of process.
Okay.
The reason to move to copper pillar, really, the driver in all of our fancy electronic smartphones and things like that we all love. There's a big push, obviously, to miniaturize and pack more functionality into those systems. So that's one of the advantages of copper pillar. You can go to tighter bump pitches, so tighter pad arrangements.
Basically, how close together they are when you say
correct,
pitch.
Right? And so that means you can fit more I/O in a smaller area and pack more fun into your gadget.
That makes sense. So does the architecture, like the word is escaping me for some reason, like the nanometer size the process that you're using dictate a lot of the packaging, or is that kind of not a thing?
There are certainly relationships. There's a big push to move to finer geometries for the IC processing and fabrication itself. Mm-hmm. That's sort of running out of steam. You may have heard of Moore's Law and things like that.
We talk about it a lot on this podcast.
Yeah. And just the investment levels to fabricate these advanced process nodes is getting out of control. So actually, it's a really exciting time in packaging because more and more investment and more research and development is going into packaging in the hopes of extending Moore's Law, doing things like die stacking, and just more integration at the package level, going to thinner die, thinner packages to make your smartphone thinner, things like that. So it's actually an unprecedented time in advanced packaging where we're seeing rapid advancement, and big companies like Intel are doing a lot, and all the what we call OSATs, the overseas assembly and test houses, are investing more, and even the fabs actually are getting into packaging. Yep.
Really? So like that's a service that they would offer instead of just fabricating. They would say, hey, we'll fab and package it, and then just send you kind of a final tested chip.
So yeah, so I was explaining flip chip. So flip chip, right? You would flip the die, and then you would interconnect it to some kind of substrate. Here's an example of an organic substrate. This is one of our ASICs that's actually in the new GMAX oscilloscope.
Okay, the new UXR.
UXR, thank you. Yeah,
no worries.
I should use the proper terms there.
No, it's fine.
So this is what's called an organic buildup substrate, and this is a way of basically, it's kind of like an interposer. It's a way of fanning out the signals from the flip chip bumps.
Okay, so an interposer, so like in the test world, an interposer historically for like PCIe, you'd have your PCIe device and your receiver, and you could stick an interposer in between and basically tap out signals. Yeah,
it's similar in that we're fanning out the I/O to a bigger aspect ratio, bigger balls. In this case, we call it Bga balls that would then interconnect to your printed circuit board, which I think more people are probably familiar with that type of technology. But the point I was getting at is that there's yet another new class of packaging that's emerged. It's called fan-out packaging, or embedded packaging. Here's an example that you cannot see, I'm sure, but
you can hold it up.
This is a fan-out package that actually is.
There's no way. Here, I'll hold it next to my watch here, and you can.
This was a critical for the UXR 33 gigahertz scopes and below that class of product.
That thing is tiny.
In this case, there are no wire bonds. There are no bumps per se. Really what they're doing here is they're taking these chips, and after they're sawn up from the wafer, and they're reconstituting them on a slightly bigger wafer on a sticky back tape kind of thing, and then they're overmolding that whole thing. Don't drop it.
I will not drop it. I know. For those of you watching, we'll post a picture of this on the Double East Talk Tech webpage, so eestalktech.com. We'll have a post up in the next couple hours for this podcast. We'll post a better picture of that. That's pretty cool looking.
Yeah, this is the lowest noise, most highfalutin amplifier that we designed for the 33 gigahertz class scopes, and this is one of the key enablers into why we can offer such tremendous value in that product, because this packaging is cheap, which is one of the main uses for it, is that it's very common in cell phone packaging where they need very low cost and very small form factor type of chips. This is our first use of this package.
Interesting.
And the point I was making about no wire bonds, no bumps, really what they do is after they've embedded these die in a mold compound, then they pattern directly off the die. So so that has advantages for us in that we can then design those traces off the die for optimal signal integrity, right? We can optimize that whole structure.
Interesting.
Yeah, and so it gives us really good signal integrity in a low-cost kind of platform, and it's been a revolutionary thing for our scopes, actually.
Huh, that's really cool. I didn't know that.
Historically, we've done things much more exotic ways. So this is a package that was used in, I think, our 90,000 series scopes. And you can see it's much more complex. It actually uses a ceramic substrate where we pattern interconnect metal conductor on that ceramic and fan that out. And you can see there are multiple well, you probably can't see.
Yeah, we'll put a picture of this one too. Basically, it's blue. Is there any reason it's blue?
It's blue because that's a buildup material. So the backside is gray. That's the ceramic. And then we actually create cavities with that blue buildup material, and then we're able to wire bond off the die onto that pattern. It's a way of creating transmission lines that are optimized for signal integrity. Again, that's a very recurring theme for us.
I've seen a trend. Yeah, it makes sense though.
And then we actually, this is something we designed and built in-house for many years, and I think still do.
We'll post a picture again. I don't know if I said that already. I think I did.
Yeah, and then the last point I want to make about this one is just that we're actually viaing all the way through this ceramic to a coaxial connector so that we can interconnect the very highest speed input to the rest of the system.
Yeah, because what good is your chip if you can't really talk to it at the speeds and integrities that you want to?
So it's all about interconnect, And, again, reliability, thermal management. This is what's called aluminum nitride ceramic, which is very high thermal conductivity.
Okay.
And also we need to worry about things like CTE mismatch, right? So the difference between the IC materials and the ceramic material needs to be matched so that when your scope heats up and cools down and vibrates and things like that, it doesn't crack or break.
That makes sense.
Yep.
Interesting. So someone actually asked in the chat. So if you have questions, put them in the chat. I'm monitoring on a computer right here. You can see my little thing. Someone asked about package composition. So you've mentioned a couple materials.
Mm-hmm.
Are there common materials that are kind of go-to for certain technologies, and then are there more exotic materials that you use for corner cases, or?
Yeah. So ceramics were used very commonly, 10, 20 years ago. And they're great because, the thermal conductivity, the ability to include many, many layers in your substrate. This is a ceramic package. You can see the green. So ceramics were commonly used. They're still used for some applications, but more recently, in the last year or so, most people or most companies have moved to organic materials.
Okay.
So if you study chemistry, you can.
I did once.
Okay.
Yeah.
There are different types of material compounds and compositions. Organic materials are more like polyimide type materials.
Okay.
And they're fabricated with the core layer. These organic substrates that I showed earlier, with a core layer that's very similar to like a PCB.
Okay.
And then from there they build up very very thin layers of organic buildup material about that core, and those can be made very thin, and they're patterned with what's called semi-additive manufacturing, and so they can be made, basically it just boils down to they can be made with smaller lines and spaces and better tolerances, which is important.
That makes sense.
Yeah.
Okay.
And it's all about fitting more circuitry into smaller areas, so any technology that allows you to do that is, and also cost, and other factors, I'm sure. But anytime a technology advances in that direction, people adopt it, and it takes off pretty quickly.
That makes sense.
Yeah, and that's what's happening with fan out now.
Okay.
Yeah.
How fast does the technology spin like that? How often do people pick it up? And
I would say it's accelerating in its
Okay.
pace of innovation in packaging because of the reasons I discussed earlier with Moore's Law. There's a whole lot more investment and development going on these days, and some of the buzzwords that I mentioned earlier, you'll hear things like 2.5D packaging, system in packaging, heterogeneous packaging, more than more packaging.
I'm going to nod my head like I know what you're talking about, but can you break some of those down for us?
Yeah, that is a class of packaging that relies on higher density interconnect.
This is the 2.5D?
With the goal of, yeah.
Okay.
So this is using things like silicon for the interposer, where let's say you have two chips that you want to interconnect with a very wide bus, and this is the case for things like high bandwidth memory.
Okay.
Thousands of chips.
So you have tons of lines coming in, and you want to talk to them all pretty much in parallel.
Yep, one chip, communicating with like SerDes type of interconnect, and in the case of HBM, which is kind of the primary driver for this 2.5D thing today, also FPGAs.
That makes sense.
They're using silicon for that interconnect layer, and then they're using technologies like through silicon vias, which is takes some advanced patterning and via formation type of technologies to be able to then interconnect with the rest of your system.
Okay.
There are other ways of doing that companies are researching using fan-out type technologies as well.
Okay.
So, yeah.
Are you familiar? We did a podcast, I don't know, maybe 5 or 10 episodes back about 3D silicon, where you basically just stack right on top. Have you looked into that at all?
2.5D is the precursor to that, right? It's similar in that you're using through silicon vias to make vertical connections.
Right.
And that's where the die stacking comes in, and you would then stack multiple die on top of each other, sometimes 4 or 5 die stacked on top of each other.
Crazy.
Yeah, it's really...
It makes sense.
The acceleration of this type of development has really led to a lot of advances in technology, and we all consume tons of data, and we're not slowing down.
I do. Yep.
We're generating some right now.
Stream live, and yeah.
So this is really popular for servers and advanced computers where a ton of data, and they need to be able to fill more memory faster, things like that.
Yeah,
so
that makes sense.
those types of industries are really driving a lot of development, advancement in
Okay.
packaging.
So that I have 2 questions about that then. One is there's got to be a thermal concern, because right now with packaging, you don't have to worry about multiple die stacked on top of each other, and that's where most of the heat's coming from, I would assume.
Yeah, Daniel, you're absolutely right.
Okay.
Thermal is one of the critical elements of package design. It's actually what makes package design really fun. And I'll do a little recruiting right now. We are hiring, by the way.
Hey, tell me about that. You have a job opening.
I do. This one is actually for an advanced type of contributor, but we're hiring pretty often these days.
In Colorado Springs, check it out. Jobs.keysite.com. Search under Colorado Springs, and maybe we'll find someone. That'd be awesome.
That would be cool. The point I wanted to make is it's really a multidisciplinary kind of job. So obviously we need electrical engineering because we're doing things like signal integrity design and routing. But we also have mechanical engineers on the team. We have material scientists. We need to be concerned about viability and things like these manufacturing processes that are very kind of niche. So my team gets to get involved with all these different kind of elements of engineering, and it really encompasses a lot. And then we obviously get to work on integrating those packages in the rest of the system, so we get to work with the rest of the hardware design teams. It's a really fun job. I love it, as you might be able to tell.
Yeah. We may have to take, I know you have a test lab just like down the hall. We may have to take a little tour of that at some point.
Sure.
Blur out all the proprietary stuff.
Yeah, you have to pull
That'd be fun.
Pull in one of the test people to give you a overview of what they do, because it's interesting work as well. Obviously, we need to, after we build these ASICs, we need to test them, make sure they're working well, and design for that as well.
Yeah. So how do you? Designing for tests is maybe something to talk about. How much do you interface with the test team?
I mean, we work in close partnership. We're under the same organization. So there are overlaps abound in the digital and system, or the digital and verification aspects of the chip design, then the physical design of the chip, the packaging, and the design for test, and then also the production test system development. So all those, we work hand in glove with those.
Okay.
Those people.
Great. Someone put a question in chat. Will this new packaging affect logic characteristics or increase speed of logic families or technologies? So I'm going to take that a step further and say, what is driving speeds now? Is it packaging? Is it the I keep forgetting the word, the nanometer sizes and the processes?
Yeah.
Or is it a shared responsibility?
Yeah, so that's a great question. It's all of the above. Certainly, when you're on the IC, you're dealing with very small geometries, and so the smaller the geometry, typically the lower the parasitics, right? And so if you need to design a high-frequency path through the IC, you can do that, but you do need to worry about things like capacitive loading from things like ESD structures, those kind of things. And this is typically in the analog world, the type of design you would work. So all of these engineering principles apply in whatever node you're talking about. But one of the critical areas is the transition. Anytime you have a major transition in your signal path, you open yourself up to reflection loss, right, or mismatch.
That makes sense.
So one of the critical areas there is the bump transition or the wire bond transition or whatever type of packaging you're using. So we use modeling tools like Keysight's EM Pro and ADS.
Hey, we're giving away ADS as part of Wave on Friday, a 1-year license. So if you haven't signed up, go check it out.
Very powerful tools. We use them very regularly.
They're pretty rad.
So we have to, if you study RF and microwave type of design, you know that you have to match these circuits, and you have to try to compensate these mismatches as best you can. And the higher frequency you go, the more difficult it becomes to do that.
Okay.
You run into manufacturing limitations and tolerance issues and things like that.
That makes sense.
Yep. And then when you're trying to move a signal, like a digital signal, using SerDes or something like that across a fairly long distance, you exposed to losses and again reflections and things like that we design or we use equalization type of circuitry for that.
Okay.
So you can compensate, you can peak your signal so that you are basically compensating for those losses.
You can basically pre-distort your signal to account for the losses that you're going to get.
Correct. Yeah.
Yeah.
Yeah,
Okay.
that's a good way of describing it.
Okay.
And then the other thing that's happening is, as we try to move more data across a single channel, there are new technologies and approaches for that. Things like multi-signal leveling, PAM4. So instead of just
Talk
using
about that.
Okay.
There's a link. Check
Cool.
it. We'll put a link. Yeah.
So yeah, instead of just using 2 discrete states, you use more states and you can
Right.
move more data. But yeah, those are also things that my team gets involved with, modeling those channels and then modeling the actual signal propagation.
That's cool. So, and I assume this is kind of a silly question, but you the chip is so tiny, and then you put it on this. If I can snag this, you put it on this big old chip. Why not just make a bigger chip? Like, we drive the sizes down, the gate sizes down and down and down, but then we put it on a big old thing.
Well, that really is primarily a cost aspect, right? So again, you're moving to smaller geometry nodes. The complexity of actually fabricating those wafers becomes more and more, and so the costs become more and more, and so the economies of scale become really, really critical, and they're always a challenge for us because we're not a super high volume, maker of chips like some other
Right.
chipset type of companies.
Yeah, people making like Intel making a processor. There's going to be a lot of those. Yeah.
Yep. So really, the more chips you can fit on a wafer, the cheaper the die cost.
Okay. Yeah, that makes sense.
That's probably a primary thing, and then just the physics of it. Also, bigger things are less reliable. So there is a limit to die size that you can realistically attach to one of these kind of substrates and not have TCE and bump cracking or other kinds of problems, or more commonly the dielectric layers on the IC itself are very fragile, and so you need to minimize those stresses.
Okay, so a smaller chip, less stress.
And we model that too. So we'll model those mechanical stresses as well. Yep. And
so what are common failure points you look for as you're designing, or that you have to build against or design against?
Yeah, so we try to stay in the sweet spot. We have not had a major reliability issue in packaging for a while. Because
for a while? No, we're not.
We've certainly had our issues in the past. That's part of the reality of R&D.
Yeah.
But we've tried to settle into more of a sweet spot type of design where we're designing into our vendors, kind of the zone, the envelope of qualification where things are reliable. But it's things like I mentioned, like the bump stresses and die cracking are the big ones. Thermal issues, so we model thermals as well. So I can show you kind of a little bit. This is a better one to use. So you can.
We'll probably just upload a photo of this whole case because it's just a box of goodies. It's a box of goodies, yeah.
It's fun.
This is Jesse's resume. He's just like, this is me.
Packaging can be very hands-on, whereas other elements of design live in the computer.
The poor netless guys are like, look, here's a file.
But hey, that's definitely a exciting and
for sure.
innovative area of design as well. But for thermals, you can maybe see, and maybe anybody who's ever built their own computer knows about
vertical with it there.
Okay. Anybody who's ever built their own computer knows about the thermal interface materials. This white gunk on the die is meant to enhance the thermal dissipation through silicon, actually a pretty good heat spreader. But then we use a very thin layer, thin to win, layer of this interface material to a nickel-plated copper heat spreading lid, which helps to then move the heat through whatever you want, a heat sink or a fan or something like that.
Okay, so it's like a pre-heat sink.
Yeah. It's another layer.
Interesting.
Of the interface.
So I always thought about just heat sinks. I never thought about anything further than that. So
these are all critical elements of the whole dissipation path. So yeah, that's another thing we worry about. Our chips, we are packing a ton of functionality and very high performance. With high performance comes power dissipation.
For sure.
And we're always trying to manage that, and we're always trying to push the envelope to realize the most functionality that we can in our systems and integrate and provide the most killer products we can. And it's
working.
Yeah, that's another big part of it.
Awesome. Someone asked Yagia in South Africa, I think. Hey, what are your views on-chip memory?
We use it regularly.
From a packaging standpoint, are there extra considerations you have to take in, or just kind of standard?
I guess the big thing would be the die size. So this chip, this is the DSP engine, memory management engine for the UXR.
Okay.
I've been referencing a lot.
And that's probably like the chip itself looks to be like 3/4 of an inch by 3/4 of an inch.
Yeah.
And the package is maybe like 2 inches by 2 inches or so.
I live in the.
Oh, and yeah. Well, if you know the answer,
it's like 17 millimeter square, 17, 18 millimeter square die.
Okay.
Or on a side, and then a 50 millimeter on a side
Okay.
package. Yep.
So more than double.
Yep. That's just because of the sheer number of I/O. I haven't showed the backside.
Yeah.
This is the Bga Array. So
it kind of looks like metal sandpaper a little bit.
Yeah.
If I were to describe it for the audio.
Do a little exfoliation.
You can mess up someone's car with that, right?
So you can't see it, but the die actually has over 10,000 bump interconnects.
Holy moly.
And there are thousands of ball interconnects here. So, a lot of these are power and ground supply.
Okay.
So we use a lot of those interconnects to optimize the power delivery network. It's yet another area of design that we have to be concerned about.
You can't just pipe in one, power source and say, hey, it's good, the rest of the chip will run off this. Like, you have to spread it out.
Yep, so power supplies are vulnerable to all of the same kinds of power integrity, in this case, issues associated with parasitics like inductance and capacitance. So generally, more balls is better. We use big planes in the package to carry the supplies, supply currents, and then we use bypass capacitors on the package as well, and on the board and on the chip. To manage that, and basically you're trying to minimize droop and ripple and things like that on your supply.
Makes sense.
Yeah. So
there's a lot of thought and a lot of engineering that goes into just the packaging.
Yeah, definitely. What was the original question? I'm not sure. If
on-chip memory.
On-chip memory. Yeah. So this chip has on-chip memory, and it makes the die bigger, which is a negative because it drives up the die cost and also the yield. That's another element of why you want to try to keep your die size smaller, is that every wafer is only going to yield so much of the die on it, and so the bigger it is, generally the lower the yield.
And then so basically when you're fabbing the chip itself, it's on a wafer, and there's a bunch of chips, and then you go in and test them and saw them up, but then based on where they are on the wafer and the quality of the materials, there's only a certain percentage of them are going to actually work. That's
correct.
So the smaller they are, the more likely that there's not like a weird in the material, or they're more centrally located.
Yeah. Generally, die towards the center of the wafer yield better. Die on the outside, and that just has to do with the patterning and processing aspects. Smaller die tend to yield better. And I was going to make another point, but it's escaped me now.
Fair enough. It comes to you. Let's see. How much gold material is used? And then are there any other exotic materials? We've seen people try to recover gold from chips and part of e-scrap thing.
Yeah. The package I showed earlier.
Where's the gold in this building? That's the real question. Just kidding.
In very
I know it's
guarded,
locked up.
Security team.
In the vault.
So we actually do that. We have an in-house process where we're patterning thick film gold and other materials like resistors and dielectrics, such as in this package, on ceramics. And we do recover that. Gold is still used very commonly for wire bonds, although people are using aluminum for current carrying capacity and cost reduction reasons.
That makes sense.
A lot of interconnects in these other types of flip chip packages is copper-based. And so we need to use a metal system that is compatible with the die metal system in the bumping.
Okay.
So things like copper, nickel, titanium layers, very thin for metal migration types of protection. So
Yeah, and we're pretty much out of time. So is there anything else that you want to hit? I know it goes by. Yeah, that's what all our guests say as I hit my face on the microphone. Are there any other topics or buzzwords that you wanted to hit before we call it a day? You got a whole bunch of goodies there, so I can see you weighing the possibilities.
I think I covered a lot of the topics that I wanted to cover. You can email us if you've heard a buzzword that I didn't. Each vendor has their own terminology too, so you'll hear things like QFN packaging, flip chip BGA packaging, EWLB. There's just a lot of terminology. So I think we have some mechanism for people to reach out. They can ask us those kind of questions. Is that something that
you can just put comments in on this or on the WC webpage or on Facebook, or you can ask me on Twitter at keysite_Daniel.
I'm not on Twitter.
A lot of people aren't, but people that are very much on Twitter. So I'm intermittently on Twitter, but I get push notifications, so you can, bug me directly if you want. So if you ever can't find me in the office and play some disc golf or go mountain biking, you can.
We should go out
hit
and try
me
and
up
play
on Twitter.
right now.
Oh my gosh, it's like 30-mile-an-hour winds.
Complete
and
whiteout.
Yeah, it's not pretty. At the end of every podcast, we like to ask our guests a stupid question. So my stupid question for you is going to be something. What was your favorite? If you were to give someone a gift, what was your favorite package or packaging?
A box of chocolates.
So if you were going to give someone a box of chocolate, a box then, or would you?
Okay, no, I'm joking. So if I was to give like a gift of
no,
ASICs?
not ASICs. Like if you're giving someone a birthday present, what's your favorite? Do you have a
Favorite
go-to
gift?
like wrapping paper? Do you do the bag with the tissue paper?
No, it would be in like an unmarked cardboard box with like some styrofoam nuggets in there.
Okay.
And then something silly.
Okay.
Probably.
From the packaging expert, unmarked styrofoam box or unmarked box with styrofoam popcorn.
Yeah, and
You
then
heard
you
it here
put like a
first.
hammer on top, and then you put like the chocolates on bottom, right? Because everybody,
Right.
they open their package, they take out the gift, and then
okay.
they keep digging, right?
So you
always
like the
gotta
gift
empty
within
it
a
and make sure
gift?
there's nothing
Are
else
you
in
the
there.
guy that like does a box and a box and a box and a box?
I
just
like to give gag gifts, and,
Yeah.
and if it's for a sweetheart, then you gotta
Right,
make
right.
it silly and fun.
Okay. Do you have a favorite gag gift story? I'm gonna put you on the spot.
Oh, geez.
If
Why
not,
didn't
that's
you
okay.
prime me?
It just didn't come. It didn't occur to me before we started that I might ask you about what gag gifts you've given.
Gag gift. So when I was a kid, I was really into magic.
Okay.
When I was like in
Like
middle school.
magic tricks,
Right,
not
yeah.
like Magic the Gathering.
So I did magic tricks.
Okay.
Like every 12-year-old boy, I guess.
yeah.
So I did one time give somebody one of those like popcorn things with like the snakes that.
Oh,
pop
yeah,
out of
yeah,
it.
yeah.
I think I gave it to my grandma, and I think
Oh,
she
no.
almost had a heart attack.
Uh-oh.
So that was, but we had a good laugh afterwards. Yeah. So
Awesome.
that's what popped into my head.
That's a good one. Okay, so we're going to call it a day. Make sure to subscribe to the Keysight Podcast YouTube channel. You can also check us out over on Keysight Labs. And you can also subscribe to this podcast in your favorite podcast delivery system because we do it as an audio version as well. We are streaming live. If you liked it being live, then let us know. Put it in the comments, put it in chat, and we'll try and do it again. This is something that we've been wanting to do for a long time, and it's kind of just like, what the heck? We'll just give it a go today and see what happens in the middle of a snowstorm with nobody around. So I'm going to hit stop streaming on YouTube. I don't know how fast it's actually going to stop. So if you're watching, thanks for watching. If you are